Hello, linear algebra student. This video is for chapter 4.2, part 1. We're going to talk about three things. The first two are most important. We're going to introduce two subspace of Rn. First is called null space, and the second is called a column space. Both of them related to a matrix A. So what's this matrix about? This matrix is related to a linear transformation. Okay, so if I have a linear transformation called T, where I send x to AX, and then A is the standard matrix that map x to AX. So we talked about this in chapter 1. So because A by default is M times N matrix, so I have M rows and N column. So this X would be like those weights that combine the columns of A into a new vector. So X is Rn. X is Rn. And then after you do the transformation, it become AX is in Rm, right? Because you have M row. So basically it is a transformation that goes from Rn to Rm. Okay, so and then we recall in chapter 1 we also talk about the special systems of equation. It's called homogeneous system, where if I have a matrix A and I times x is equal to 0, then the set of all these x that make AX equal to 0 is a set of vector in Rn also. So this set of vectors, if we put them together, they have a set, and we call this set of vector that when you plug into the linear transformation, the output is 0. It's called the node A. Node A. So it defines node A as all the x in Rn such that A times x is 0. And you can think of T being the transformation. If you get this x in node A, you map T to it by doing AX. It becomes 0. So that means this transformation map all these x called node A into the 0 vector. So this is like maybe the different one of them, but they all maps into 0. Okay, so we call them the null space. Now I use the space here. So are we sure that it is a space? It is just all those x that after I do the transformation is equal to 0, right? So it is indeed a space. And then we'll talk about, so here, question is now a vector space or a subspace or a subspace of Rn. So first, the few things that we want to talk about is if I have this A matrix, is 2, 4 in the null space of A? So notice 2, 4 are the weights. Okay, so 2 times is kind of like the linear transformation. 2 times of this plus 4 times of this equal to 0. Is this true? So to check if W is in the null space, we just have to check by doing the multiplication, right? Check by 3, -2, -10, -6, 4 times 2, 4. See if it is equal to 0. Okay. So we know that matrix multiplication like this means linear combination, right? 2 times of 5, 3, -2, or you can actually do the real multiplication, matrix multiplication, but I'm just going to do the linear combination. It's easier to check. Is it? So 4 times the second one. So this means 2 times of the first one is 10. 10 plus -40, right? Because it's 4 is this set. So it is not. So it's just -30. And then 2 times 2 2 times 3 is 6. 6 minus 24 is not 0, right? 6 minus 24 is negative 18. And then 2 times negative 2 is negative 4. 4 times 4 is 16. So it is only 12, right? So not equal to 0. So this 2, 4 is not in null A. Okay, so null A is defined as all those matrix when you are transformed by the matrix A is 0. So the second theorem is actually the null A is a space. It's a subspace of Rn. And actually all the solutions to Ax equal to 0 of an M homogeneous linear equation in n unknown is a subspace of Rn because A is actually equivalent to this M homogeneous equation. So the reason why it's a subspace is what it can be. We can write it as a linear as a spanning set. We can write the spanning sets, and we know that if we have a spanning set for it, it is automatically a subspace, right? So we can do it this way, and also the second thing is 0 is in AX in null A. Why? Because A times 0 is 0. So 0 is the trivial solution is always in it. We can also actually prove it by saying if x1 is in null A and x2 is in null A, or well, let's say v1 and v2, okay, because x1 in null A, then v1 times A is equal to 0. V2 times A is equal to 0. They are still equal to 0. So so V1 plus V2 times A would equal to 0, right? And lastly, we can also say if I have a constant then multiply by 2V1, would it be in the null? Because it would be C times V1A, which is actually equal to C times 0. So it's 0. So this show that it is a subspace. Okay, look, so and of course it is hard to prove this 3, right? So usually what we did would be to find the spanning set. So usually this is the main thing that we do. And let's review how to find the spanning set of anything. So for example, I have a set of ABCD R4 matrix, a subset of R4 matrix that satisfy 2 requirements. So use theorem 2 to determine if H is a subspace. So theorem 2 that it belongs to a systems of equations of a null equation. So if I write this out, it would be A minus 2B plus 5C minus D. If I move the D over, equal to 0. And also 0A, negative A, 0D plus C. Oh, minus B. Move the B over. The B is over here. And then there's no D, right? Equal to 0. So we can say that, oh, this is a systems of equation. So where A is equal to the coefficient matrix, 1, negative 1, negative 2, negative 1, 5, 1, negative 1, 0. And so ABCD is in the null space. So the sets ABCD is in the null space. So this set ABCD satisfying this will be in null A, right? So because it's in null A, so it is a subspace by theorem 2. And actually, we will actually also find the spanning set. Example 2, determine if this is a subspace or not. So let's see. Can I write a matrix? Okay, so this set is A minus 2B, and then A, and then B. Can I write this as a subspace? Well, I can write it as A 1 1 0, right, plus B -2 0 1, right? So this set, so H is spanned by these two who is not CD, is AB. It's spanned by the set of 1 1 0 and also -2 0 1. So it is spanned by linear combination of this, and we know that. And is 0 0 in H? So it is a subspace because 0 0. If you can write the spanning set, but it is all of them are linear combination of this, including 0 0. So yeah, so because H is a spanning set with the matrix of two vectors. So it will satisfy all those subspace things. Now this one has nothing to do with null A. It is this one that has things to do with a null A. This has nothing to do with another space called just say spanning sets. And later on we'll define something called column A. Okay, so exactly how do I find a spanning set for null space of A? Now that I know that, oh, actually it belongs to a null space of A, and by theorem 2, we know that it is a subspace, but how do I find a spanning set if I want to? So this means that you want to solve all the equation of the homogeneous equation of AX equal to 0. To find it, you actually have to augment the columns of A with 0 because you're solving a homogeneous equation. Do the RREF of this augmented matrix. Write the solution in free and basic variables. Then rewrite them in parametric vector forms. And then the vectors are in the spanning set. So let's do an example. So I have this A here. Find the description of null A by listing the vector that span it. Okay, so so that means I need to do step 1 will be I write all of these together. These are the equation AX because it's null space of A, so that means AX equal to 0. I'm solving this -7, -1, -4, 0, 0, 0. The B is 0, 0, 0. And then I'm going to do a augmented matrix. I already put it in here. -7, -1, -4. And I do a reduced row echelon, it becomes this. So 1, -2, 0, -1, 3, 0. So use the calculator to do the reduced echelon of 1, -2, 0, -1, 3, 0, 0, 0, 1, 2, -2, 0, and then I think the n is all 0. The last one is all 0. So I'm able to write the solution. So of course this is all, the last row is always 0. So the solution that you have would be this is a basic column, this is a basic column, and that's it, right? X1 and X3, all the others are free. So I'll say X1 is equal to what? So X2, X3, X4, X5, right? X2, 2, X2 minus plus X4 minus 3, X5. X2 is free, X2 is X2, X, not be able to finish. So I'll continue it in the next section.